Tonight, we're going to examine a dream that may never come true. The nearest star to our sun is just 4.24 light-years away. That sounds close. But even if we launched our fastest spacecraft today, it would take more than 70,000 years to arrive. And distance is only the first problem. There are 5 reasons we may never reach the nearest star. By the end of this journey, you'll understand why the barrier isn't just technological. It may be built into the universe itself. The nearest star feels close enough to imagine. Close enough to believe that with better engines, better fuel, or enough patience, we will eventually get there. But as we begin to unpack the numbers, something shifts. The problem is not just that Proxima Centauri is far. It's that everything about reaching it scales beyond human terms. The distance stretches beyond a lifetime. The energy exceeds practical limits. And even if those obstacles were solved, deeper structural boundaries remain. Before we go further, if you enjoy calm, long-form explorations of space and the limits of reality, consider subscribing. It helps this channel continue making these journeys possible. Now, let's begin. To understand why we may never reach the nearest star, we have to stop thinking in ordinary distances. On Earth, distance is manageable. 1,000 kilometers is a long drive. 10,000 kilometers is a long flight. Even traveling around the world is measured in hours, but space does not scale that way. A light year is not simply a large number of kilometers. It represents how far light travels in 1 year, moving at nearly 300,000 kilometers per second. In 12 months, light covers almost 9.5 trillion kilometers. Multiply that by 4.24, and you arrive at more than 40 trillion kilometers between us and Proxima Centauri. Numbers at that scale lose meaning, so it helps to compress the model. Imagine the sun as a small marble sitting on a table. On that scale, Earth becomes a grain of sand orbiting a few meters away. The outer edge of our solar system would stretch perhaps the length of a football field. Proxima Centauri would not be across the table. It would not even be across the city. It would be thousands of kilometers away. The emptiness between stars is not decorative darkness. It is the dominant feature of the galaxy. Even our fastest machines struggle against that emptiness. Voyager 1, launched in 1977, has traveled for nearly half a century. It has crossed the boundary of the solar system and entered interstellar space, and yet it has not traveled even 1% of the distance to the nearest star. At its current speed, Voyager would need roughly 73,000 years to reach Proxima Centauri. That is longer than all of recorded human history. It is longer than agriculture. Longer than cities, longer than writing. So the natural response is to think about speed. If distance is the problem, then speed must be the solution. Build a faster engine, burn more fuel, accelerate harder. But speed is not simply a matter of engineering ambition. Rockets must carry their own fuel, and fuel adds mass. More mass requires more fuel. The relationship compounds quickly. The faster you try to go, the more dramatically the required energy increases. The rocket equation is not forgiving. It does not bend for optimism. And beyond that equation lies a more fundamental constraint. The universe enforces a speed limit, the speed of light. Nothing with mass can reach it. As an object accelerates closer to light speed, the energy required to continue accelerating grows dramatically. To reach light speed would require infinite energy. That is not a technological shortcoming. It is a property of reality itself. Even if we imagined reaching 10% of light speed, Proxima Centauri would still be more than 40 years away. 40 years in transit. 40 years exposed to radiation. 40 years isolated from Earth. And if travelers returned, decades would have passed at home. At higher fractions of light speed, time dilation would distort the experience even more. The traveler might age only a few years, while entire generations pass on Earth. Reaching the nearest star would mean losing the world you left behind. As these numbers accumulate, a pattern begins to emerge. The challenge is not only technological, it is biological and temporal. Humans are built for decades of life, not centuries in transit. Radiation exposure over long durations poses serious risks. Psychological stability over multi-generational voyages is uncertain. Generation ships have been proposed as solutions, vast self-contained habitats traveling slowly between stars, but even these introduce complex social and mechanical vulnerabilities. And yet distance, energy, and physics are not the only barriers. The universe itself is expanding. On cosmic scales, space stretches, carrying distant regions farther away. While Proxima Centauri remains gravitationally bound within our galaxy, the larger structure of the universe reminds us that not every destination remains accessible forever. Some regions are already receding beyond any possible reach, no matter how patient we become. The nearest star tempts us because it feels attainable. 4 light-years does not sound overwhelming compared to the 100,000 light-year span of the Milky Way. But for creatures whose lifetimes rarely exceed a century, 4 light-years is enormous. It reveals a mismatch between human scale and cosmic scale. The universe operates in millions and billions of years. We operate in decades. Tonight, we will examine the 5 barriers standing between us and that single point of light. Distance is the first. Energy is the second. Physics imposes the third. Biology confronts us with the fourth. And finally, the architecture of the universe itself presents the fifth. Together, they form a boundary that may not simply be difficult to cross, but fundamentally resistant to our ambition. For now, let that idea settle. Above us, the stars remain steady and silent. Proxima Centauri continues to shine, 4.24 light-years away. It appears close enough to matter. But as we move forward, we will see why that closeness may be an illusion born of perspective, and why the journey to the nearest star may test the limits of what it means to be human. If distance were the only obstacle between us and the nearest star, the solution would be straightforward. We would simply build faster engines. Humanity has always responded to distance with speed. We crossed oceans by building larger ships. We shrank continents by inventing aircraft. We escaped Earth's gravity by building rockets powerful enough to break free of it, so it is natural to assume that interstellar travel is simply the next engineering challenge. If Proxima Centauri is 40 trillion kilometers away, then the answer must be to travel faster. But speed in space does not behave the way we expect. On Earth, accelerating a car requires more fuel, but the relationship is manageable. In space, the relationship between speed and fuel becomes exponential. Rockets do not push against air or ground. They must carry every kilogram of fuel they will ever use, and that fuel has mass. The more fuel you carry, the heavier the spacecraft becomes. The heavier it becomes, the more fuel you need to move it. This feedback loop grows rapidly. It is described by what engineers call the rocket equation, and it imposes brutal constraints on how fast a spacecraft can realistically travel. To double your velocity does not simply require double the fuel, it requires significantly more. To increase your velocity tenfold requires an amount of fuel that quickly becomes impractical. At some point, most of your spacecraft would consist of propellant rather than structure or payload. The craft would be little more than a tank of fuel pushing itself forward. Even then, the speeds required to reach another star within a human lifetime are far beyond what chemical rockets can provide. Chemical propulsion, the kind that carried humans to the moon, is powerful but limited. It is sufficient for escaping Earth and exploring our solar system, but it is entirely inadequate for crossing interstellar space. Even nuclear fission rockets, which have been studied in theory, would struggle to reach a meaningful fraction of light speed. Fusion propulsion, often proposed as a more advanced option, remains experimental even for stationary reactors on Earth. Harnessing controlled fusion in a compact, reliable space-qualified engine remains a challenge we have not yet solved. Then there is antimatter propulsion, frequently invoked in science fiction as a near-perfect energy source. Matter and antimatter annihilate each other upon contact, releasing enormous energy. In principle, antimatter engines could achieve extraordinary velocities. In practice, we have only produced tiny amounts of antimatter in laboratory conditions, measured in nanograms. Storing it safely for long durations is itself a massive challenge. Producing enough antimatter to propel a starship would require energy on scales that exceed our global production many times over. Even if we imagine some breakthrough propulsion system capable of accelerating a spacecraft to 10% of the speed of light, we would still face staggering realities. At 10% of light speed, Proxima Centauri would still be over 40 years away. That means 40 years of continuous travel, continuous exposure to radiation, and continuous system reliability. And that is only one way. A return trip would double that duration. For a human crew, such a mission would span most of a lifetime. But velocity introduces another, less intuitive problem. As an object moves faster and faster, its kinetic energy increases with the square of its velocity. Doubling speed does not double energy demand, it quadruples it. Approaching light speed causes energy requirements to climb toward infinity. The closer you attempt to reach the speed of light, the more dramatically the required energy rises. This is not a matter of engineering inconvenience. It is a consequence of Einstein's relativity. The universe does not allow objects with mass to reach light speed. So perhaps we do not need to reach light speed. Perhaps even a fraction would suffice. But fractions are still unforgiving. To accelerate a multi-ton spacecraft to 10% of light speed would require energy comparable to the total annual energy output of entire nations. And that energy must not only be generated, but directed safely and efficiently. Every inefficiency translates into heat, structural stress, and additional mass. Even if we solve propulsion, there remains the issue of deceleration. Reaching Proxima Centauri at extreme speed is only half the challenge. To enter orbit around another star, you must slow down. That requires additional fuel, additional energy, and additional mass. Otherwise, you would simply pass through the system at extraordinary speed, unable to stop. The energy wall reveals something fundamental. Interstellar travel is not simply about ambition or ingenuity. It is about scale. The energies required to meaningfully shorten the journey between stars are on a level that stretches our current technological and economic frameworks. It would require sustained, coordinated global effort for decades or centuries, with no guarantee of success. There's also the matter of collisions. Space between stars is extraordinarily empty, but it is not entirely devoid of matter. The interstellar medium contains sparse atoms of hydrogen and helium, along with microscopic dust grains. At Voyager's speed, these particles are harmless. At 10% of light speed, even a tiny grain of dust carries enormous kinetic energy. A particle the size of a grain of sand impacting at relativistic speed would release energy comparable to an explosive. Shielding against such impacts over decades of travel would require heavy protective structures, which add mass, which adds energy demands. Radiation poses another continuous drain. Galactic cosmic rays, high-energy particles from distant supernovae and violent cosmic events, permeate interstellar space. Even within our solar system, Earth's magnetic field and atmosphere shield us from much of this radiation. Beyond the heliosphere, exposure increases. Over decades, radiation damage to electronics and biological tissue accumulates. Designing systems capable of surviving such environments without maintenance becomes an additional engineering burden. And all of this assumes flawless operation for decades. No resupply, no repair facilities, no external assistance. A spacecraft traveling between stars must function autonomously, reliably, and redundantly for generations. The farther it travels, the longer communication delays become. At 1 light-year distance, a signal takes an entire year to reach Earth. Real-time control becomes impossible. Every system must anticipate failure and adapt on its own. As we continue this exploration, notice how each attempt to solve one barrier introduces another. Increase speed and energy requirements multiply. Add shielding and mass increases. Increase mass and fuel demand rises. Accelerate to extreme velocities and microscopic dust becomes lethal. Attempt to shorten travel time and relativistic effects distort time itself. The dream of reaching the nearest star does not collapse because of one insurmountable obstacle. It strains under the weight of many interconnected limits. Distance pushes us toward higher speed. Higher speed demands energy beyond current production. Energy generation introduces mass and engineering challenges. Mass demands more energy. Physics imposes ceilings that cannot be bypassed. And we have not yet discussed biology in detail, or the psychological strain of isolation. or the structural limits imposed by the expanding universe. For now, it is enough to recognize that propulsion is not merely a technical challenge. It is an energy problem on a cosmic scale. The nearest star feels close in the sky. It glows gently, indistinguishable from the thousands of others. But when we translate that faint point of light into energy equations and engineering constraints, the journey begins to look less like a bold leap forward and more like a confrontation with the limits of what our civilization can sustain. Distance was the first barrier. Energy is the second, and beyond energy lies something even more absolute, the speed limit of the universe itself. In the next section, we will step into relativity and examine why even if we could generate unimaginable power, the structure of spacetime may still deny us passage. Take a slow breath. The stars above remain steady. Proxima Centauri has not moved, but as we peel back each layer of reality, the path toward it grows narrower. If distance challenges us and energy strains our capacity, physics delivers the most uncompromising limit of all. There is a speed beyond which the universe does not allow matter to travel. That speed is light. In empty space, light moves at nearly 300,000 kilometers per second. It circles the Earth more than 7 times in a single second. It travels from the Sun to our planet in about 8 minutes. It crosses the distance to Proxima Centauri in a little over 4 years. For centuries, scientists suspected that light traveled incredibly fast, but it was not until the late 19th and early 20th centuries that its true role in the structure of reality became clear. When Einstein formulated the theory of special relativity, he revealed something astonishing. The speed of light is not just fast, it is fundamental. Nothing with mass can reach it. This is not a technological problem. It is not something we can overcome with better materials or more powerful engines. It is a structural property of spacetime. As an object accelerates closer to light speed, its energy does not increase in a linear way. It increases dramatically. The closer you approach the speed of light, the more energy is required for each additional increment of velocity. At the limit itself, the required energy becomes infinite. That means reaching light speed is impossible for any object with mass. This realization shifts the discussion entirely. Interstellar travel is no longer about achieving a magical threshold. It becomes about fractions. What if we could reach 10% of light speed, 20%, 50%? Even these fractions represent extraordinary achievements, but each comes with profound consequences. At 10% of light speed, the journey to Proxima Centauri would take about 42 years from Earth's perspective. That is already within the span of a human lifetime. Yet to achieve that velocity, a spacecraft would require staggering amounts of energy. And even if we imagine that we could somehow generate and store that energy, another phenomenon begins to matter: time dilation. As an object moves faster through space, time slows down for that object relative to stationary observers. This is not science fiction. It has been experimentally confirmed with atomic clocks flown on aircraft and satellites. The effect is tiny at everyday speeds, but it becomes significant at relativistic velocities. At 10% of light speed, time dilation is modest. At 50%, it becomes noticeable. At 90%, it becomes dramatic. A traveler moving at 90% of light speed would experience time passing at less than half the rate of someone on Earth. At first glance, this seems like an advantage. If time slows down for the traveler, then perhaps the journey feels shorter, but this introduces a painful asymmetry. Suppose a crew travels to Proxima Centauri at 90% of light speed. From their perspective, perhaps only a few years pass. From Earth's perspective, decades pass. If they return home, they may arrive in a world that has aged far beyond them. Families will have grown old. Societies will have transformed. The travelers would be temporally displaced from their own origin. The faster you go, the more severe this separation becomes. Approaching light speed compresses the traveler's experience of time, but stretches the timeline of everything left behind. Reaching another star within a human lifetime may mean surrendering any hope of meaningful return. And even if we accept that sacrifice, relativistic travel introduces further complications. Length contraction, another consequence of special relativity, means that distances shrink in the direction of travel for the moving observer. To the crew, the journey appears shorter than it does to observers at rest, yet this effect does not eliminate the need for immense energy. The ship must still be accelerated to those velocities, and acceleration itself requires sustained thrust and enormous power. There is also the practical matter of deceleration. Reaching another star system at extreme speed is not enough. If you arrive traveling at 90% of light speed, you cannot simply stop by applying the brakes. You must expend just as much energy slowing down as you did speeding up. Otherwise, you will pass through the system in a matter of hours, unable to explore or settle. The total energy requirement for a round trip doubles. Every fraction of light speed demands exponential increases in fuel and engineering resilience. As velocities increase, another hazard intensifies. The interstellar medium, though sparse, contains atoms and dust particles. At relativistic speeds, even a microscopic particle becomes dangerous. A grain of dust striking a spacecraft at a significant fraction of light speed carries tremendous kinetic energy. Shielding against such impacts would require thick protective layers, which add mass, which increase energy demands, which complicate propulsion. The faster you travel, the more violent the universe becomes. Radiation effects also escalate. At high velocities, interactions with cosmic rays and interstellar particles generate secondary radiation inside the spacecraft. Even if we could protect electronics and structural components, protecting human tissue over decades of exposure remains uncertain. Biological systems are not built to withstand continuous high-energy particle bombardment without degradation. All of these factors converge on a sobering conclusion. Relativistic travel is not simply an engineering milestone waiting to be achieved. It is a regime of physics where every gain in speed magnifies every vulnerability. The laws of relativity are elegant, but they are not accommodating. There is another layer to consider. The universe is not static. On the largest scales, space itself expands. Galaxies beyond our local group recede from us at increasing velocities. Some regions of the cosmos are already moving away faster than light due to the expansion of space, making them forever unreachable. While Proxima Centauri remains gravitationally bound within our galaxy and therefore not subject to this particular fate, the broader principle is clear. Distance in the universe is not only about separation in space, but about the dynamic evolution of spacetime itself. When we imagine interstellar travel, we often picture sleek starships gliding between suns. We rarely picture the energy equations, the relativistic distortions, the collision hazards, or the temporal isolation. Yet these are not dramatic embellishments. They are inherent features of the universe we inhabit. If distance was the first barrier and energy the second, then relativity is the third. It is not hostile, but it is uncompromising. It tells us that there are limits baked into reality. No matter how advanced we become, no matter how long we persist, we cannot exceed the speed of light. We can approach it, perhaps, but never cross it. The nearest star remains 4.24 light-years away. That number does not shrink simply because we wish it to. It represents a gulf that demands not only technology, but reconciliation with the fundamental architecture of spacetime. As you sit quietly and let these ideas settle, consider what it means that the universe has a speed limit at all. It suggests that some boundaries are not temporary obstacles, but structural features. They define what is possible. Distance challenged our imagination. Energy challenged our capacity. Relativity challenges our ambition. And we have not yet confronted the biological and sociological consequences of journeys measured in decades or centuries. In the next section, we will turn from physics to something closer to home. Even if we could solve propulsion and accept relativistic time distortion, could humans actually survive the journey? Could societies endure across generations in the void between stars? For now, remember this: the speed of light is not just a number, it is a boundary, and every dream of reaching the nearest star must reckon with it. Even if we solve propulsion, Even if we generated the unimaginable energy required to accelerate a spacecraft to a meaningful fraction of the speed of light, and even if we accepted the strange distortions of time that relativity imposes, we would still face a barrier far more intimate than distance or physics. The barrier is biological. The challenge is not simply reaching another star. It is surviving the journey as human beings. Human physiology evolved under very specific conditions. For millions of years, our species developed within Earth's gravity, beneath its magnetic field, protected by its atmosphere. Every cell in our body assumes those conditions are stable. Remove them for extended periods, and the body begins to change in ways that are measurable and, in some cases, irreversible. We already have evidence of this from astronauts who spend months aboard the International Space Station. In microgravity, bones lose density because they no longer bear weight. Muscles atrophy without resistance. Fluids shift upward toward the head, affecting vision and cardiovascular function. Even with strict exercise regimens designed to counteract these effects, astronauts return to Earth physiologically altered. Now imagine not 6 months in orbit, but 40 years in transit. Artificial gravity could be simulated by rotating the spacecraft, but such a structure would need to be enormous and mechanically flawless for decades. The radius must be large enough to prevent severe Coriolis effects that disorient the human vestibular system. The rotation must remain perfectly stable. Any imbalance could introduce structural stress. Maintenance over decades would require industrial capability on board. Every moving component becomes a long-term liability. Radiation presents a second, more severe problem. Outside Earth's magnetosphere, cosmic radiation becomes constant. Galactic cosmic rays, high-energy particles originating from supernovae and other extreme cosmic events, pass through matter with penetrating power. Even within the heliosphere, astronauts receive higher radiation exposure than on Earth. Beyond it, exposure increases. Over years and decades, cumulative radiation damage elevates cancer risk, degrades neural tissue, and increases the probability of genetic mutation. Shielding against such radiation is possible, but effective shielding requires mass. Water, hydrogen-rich materials, and thick protective layers can absorb some radiation, but the additional mass increases propulsion demands. The problem compounds. More shielding means more mass. More mass requires more fuel. More fuel increases spacecraft size and structural complexity. Each solution intensifies another constraint. Even if we could design adequate radiation shielding, we cannot eliminate exposure entirely. Over decades, even small doses accumulate. For a multi-generational mission, long-term genetic stability becomes uncertain. Children born aboard such a vessel would develop in environments fundamentally different from Earth. We have limited data on how embryonic development responds to chronic low gravity and radiation exposure. It is possible that reproduction would remain viable. It is also possible that subtle developmental effects would accumulate across generations. Beyond physiology lies psychology. Humans are deeply social creatures. Our cognitive health depends on interaction, novelty, environmental variation, and sensory diversity. Studies of isolation environments, from submarines to polar research stations, show that even highly trained individuals experience stress under prolonged confinement. Astronauts undergo extensive psychological screening and training, yet space agencies still monitor mood, sleep cycles, and cognitive function carefully during missions. The longer the isolation, the more carefully it must be managed. An interstellar mission would magnify isolation to unprecedented levels. Communication delays would lengthen steadily. At 1 astronomical unit from Earth, signals take about 8 minutes to travel. At the outer solar system, delays stretch to hours. At interstellar distances, delays extend to months or years. Real-time communication becomes impossible. Emotional support from Earth would become symbolic rather than interactive. A crew would know that any message they send will not be answered within the same conversational context. That psychological distance deepens over time. Generation ship concepts attempt to address lifespan limitations by assuming that entire communities will live and die during the journey. The ship becomes a world. Children are born into transit. The mission persists across centuries, but this introduces complex sociological challenges. Cultural continuity must be preserved intentionally. Governance systems must remain stable. Education must reinforce mission purpose across generations that never saw Earth. Over centuries, language evolves, values shift, and historical memory fades. The original motivation, reaching another star, may feel abstract to individuals born in a rotating metal habitat who have never experienced planetary life. Mechanical systems compound these sociological uncertainties. Closed ecosystems must recycle air, water, and nutrients with near-perfect efficiency. On Earth, failures are mitigated by access to vast external resources. A spacecraft traveling between stars cannot rely on external supply chains. It must function as a sealed ecological loop. Entropy steadily works against order. Small inefficiencies accumulate. Minor component failures cascade if not addressed. Maintaining technological civilization within a closed vessel for centuries requires not just redundancy, but onboard manufacturing capability. Raw materials must be repurposed. Critical components must be reproducible. Every failure becomes a test of systemic resilience. Even if such a system could be engineered, lifespan remains a constraint. Suppose propulsion allowed a journey of 40 years at 10% light speed. That duration consumes most of a single human life. A crew might arrive aged, with limited time to explore before returning. A round trip would exceed a lifetime. Cryogenic suspension is often proposed as a solution, placing travelers in a state of reduced metabolic activity to minimize aging during transit. Yet long-term cryopreservation of complex organisms remains beyond current medical capability. Freezing tissues without cellular damage is extremely difficult. Reversing that state after decades without cognitive impairment is even more challenging. Digital consciousness transfer represents another speculative path. If minds could be uploaded into durable computational substrates, biological fragility would become less limiting. Machines do not suffer radiation sickness in the same way humans do. They can be shielded and repaired more easily. But this raises philosophical and identity questions. Would a digital copy of a human mind retain continuity of self? Would it represent survival or replication? The biological barrier shifts into a question of identity rather than endurance. There is also the moral dimension of departure. Leaving Earth for an interstellar mission implies acceptance that return may be impossible. The crew would depart knowing they might never see their home world again. Families would remain behind. Entire histories would unfold in their absence. Over decades, Earth would change socially, technologically, and politically. Even if return were possible, it would not be a return to the same world. Time dilation would intensify that separation. The biological barrier, therefore, includes not only the body, but the bonds that define human existence. Attachment to place, to community, to memory, these are not trivial. They anchor identity. An interstellar journey requires relinquishing those anchors or accepting that they will dissolve across time. That cost is not technical, but existential. All of these factors reveal a pattern. Every attempt to solve the interstellar challenge shifts the burden elsewhere. Improved propulsion and radiation becomes dominant. Add shielding and mass increases. Simulate gravity and mechanical complexity multiplies. Extend lifespan and identity questions arise. Transition to multi-generational systems and cultural drift threatens continuity. The barrier is not a single wall, but a network of constraints. The nearest star appears deceptively close. It shines like any other star in the sky, but reaching it would require more than engineering excellence. It would require transforming how humans live, reproduce, govern, and endure. It might require altering what it means to be human at all. Even then, success would not guarantee meaningful connection to the world left behind. As we continue, distance was the first barrier, energy the second, relativity the third, and biology the fourth. Each layer deepens the difficulty rather than resolving it. And still, one final barrier remains, one that does not depend on propulsion or physiology. It depends on the architecture of the universe itself. In the next section, we will confront that final limit and examine whether, even with infinite patience and radical adaptation, the nearest star might remain permanently beyond our reach. Even if we solved propulsion, even if we mastered the energy demands required to accelerate a spacecraft to a meaningful fraction of light speed, even if we redesigned human biology to endure decades or centuries in transit, there remains a barrier that does not depend on engines, fuel, or flesh. It depends on the universe itself. The universe is expanding. This is not a metaphor, it is not speculation, it is measurable. Since the early 20th century, when astronomers observed that distant galaxies, Proxima Centauri is gravitationally bound to the Milky Way, just as our Sun is. Within galaxies, gravity dominates over cosmic expansion. The stars in our galaxy are not being pulled apart by expansion in the same way distant galaxies are. So in principle, Proxima Centauri is not drifting away from us due to cosmic expansion. But the expanding universe changes how we think about permanence. It changes how we think about accessibility, and it changes how we think about time. When we observe distant galaxies, we are seeing them as they were billions of years ago. Their light began its journey long before Earth had complex life. During that time, the space between us and them has stretched. The distance today is greater than it was when the light began traveling. That means cosmic expansion is not just background motion. It actively reshapes distance over time. Now imagine a civilization that waits. Suppose humanity delays interstellar travel for millions of years. Suppose we remain confined to our solar system, advancing slowly. On those timescales, the structure of our galaxy changes. Stars move relative to one another. Gravitational interactions alter trajectories. Proxima Centauri itself is not stationary. It orbits the center of the Milky Way, just as the Sun does. Over millions of years, stellar positions shift. The nearest star today may not be the nearest star tomorrow. The universe does not freeze in place while we plan. There is another layer to expansion that introduces a more unsettling limit, the cosmic horizon. Because space expands, there exists a boundary beyond which light emitted today will never reach us. This is not because those regions are infinitely far, but because the expansion rate outpaces the ability of light to close the gap. Some galaxies are already receding from us faster than light due to the expansion of space itself. No signal sent today could ever reach them. This creates a shrinking accessible universe. Over billions of years, more and more galaxies will cross that horizon and disappear permanently from view. Future civilizations, if they exist far in the future, may look into a much emptier sky. They may see only their local galaxy, unaware that countless others once filled the cosmos. Although Proxima Centauri lies safely within our galactic neighborhood and is not being carried beyond a cosmic horizon, the principle matters. Accessibility is time-dependent. The longer a civilization waits, the more the cosmic landscape shifts. But expansion is only part of the story. Entropy, the gradual increase of disorder, is another universal law that shapes the long future of the cosmos. Stars are not eternal. They burn nuclear fuel and eventually exhaust it. Our Sun has about 5 billion years remaining before it expands into a red giant and sheds its outer layers. Proxima Centauri, a small red dwarf, will burn much longer, trillions of years, but even it will eventually fade. Star formation itself will slow over cosmic timescales. As gas clouds are consumed and fewer new stars are born, the universe will grow darker. Energy will become more diffuse. The cosmic future trends toward lower density, lower usable energy, and greater uniformity. While these events occur on scales far beyond human planning, they underscore something important. The universe is not an infinite playground that remains stable indefinitely. Conditions evolve. Energy gradients flatten. Accessibility narrows. Even if humanity had millions of years to prepare for interstellar travel, the environment into which we launch ourselves would not remain unchanged. Stars move, planetary systems shift, cosmic radiation fields vary. Local interstellar conditions fluctuate as our solar system drifts through different regions of the galaxy. We are currently moving through what astronomers call the local interstellar cloud, a region of slightly denser gas within the galaxy. In tens of thousands of years, we will exit this cloud and enter another region with different properties. That change will alter the shape and size of the heliosphere, the protective bubble carved out by the solar wind. It will alter radiation exposure patterns. It will subtly change the environment any outbound spacecraft must traverse. Expansion and motion together reveal a deeper truth. Space is not merely distance, it is structure and motion. Now consider the psychological implication of this. When we imagine traveling to another star, we often imagine it as a fixed target, a destination waiting patiently. But over millions of years, stellar positions shift significantly. A star that is 4.24 light-years away today may not occupy the same relative position in the distant future. Our Sun and Proxima Centauri orbit the galactic center at roughly 220 kilometers per second. Over tens of thousands of years, that motion changes relative separations. In other words, even the nearest star is a moving target. This does not make it unreachable in principle, but it complicates the narrative of simplicity. The galaxy is not a static map with dots labeled and waiting. It is a fluid system of orbital mechanics and gravitational interactions. Expansion also intersects with relativity in subtle ways. As distances increase, communication delays increase. As communication delays increase, coordination becomes harder. An interstellar civilization separated by light years would function as isolated nodes, not as a cohesive society. Governance across light years becomes effectively impossible in real time. Each colony, if established, would evolve independently. Political unity across interstellar distances may be unachievable. Now imagine humanity does succeed in reaching Proxima Centauri. Imagine a colony is established around one of its planets. Over centuries, communication between Earth and that colony would be limited to exchanges separated by years. Social, political, and technological divergence would accelerate. The two branches of humanity would become culturally distinct, over longer timescales, perhaps biologically distinct. Expansion does not just stretch space, it stretches identity. But here is the key question. Does expansion itself make Proxima Centauri unreachable? On human timescales, no. The star remains gravitationally bound within our galaxy. It is not slipping beyond a cosmic event horizon. If we could overcome distance, energy, relativity, and biology, Proxima Centauri would remain physically accessible. And yet expansion teaches us something deeper about cosmic humility. It shows that access to the universe is conditional. It depends on timing. It depends on energy gradients. It depends on evolving structures. The farther we look, the more we realize that permanence is illusion. There's also a philosophical layer embedded in expansion. The universe began in a hot, dense state nearly 13.8 billion years ago. Since then, it has been expanding and cooling. The conditions that allow life, stars, and planets to exist are part of a dynamic phase. In the far future, conditions will not resemble today's cosmos. Civilizations that arise billions of years from now will inhabit a different universe. When we ask whether we will ever reach the nearest star, we are asking from a very specific moment in cosmic history, a moment where stars are abundant, heavy elements are present, and energy gradients allow complexity to flourish. We are fortunate to exist in this window, but that window is not eternal. Expansion, entropy, stellar evolution, galactic motion, these processes frame our ambitions. They do not forbid reaching Proxima Centauri, but they remind us that our timeline is not infinite. The dream of interstellar travel must unfold within the constraints of cosmic evolution. Now we have confronted 5 escalating barriers. Distance stretches beyond intuitive comprehension. Energy demands rise exponentially. Relativity imposes an unbreakable speed limit. Biology resists long-duration exposure to hostile environments. Expansion reveals that the universe itself is dynamic and conditional. Each barrier alone is daunting. Together, they converge into something heavier than any single obstacle. In the next section, we will bring these barriers together and ask the hardest question of all. Even if no single limit makes the journey impossible, do they combine in a way that effectively ensures we may never reach another star? And if that is true, what does it mean for the future of exploration and for our place in the cosmos? Stay with me, the conclusion is not despair. It is perspective, and it may change how you see the stars above you tonight. Individually, none of the barriers we have examined appear completely absolute. Distance is enormous, but not infinite. Energy requirements are staggering, but in theory not unattainable. Relativity prevents us from reaching light speed, yet it still allows travel at meaningful fractions. Biology resists hostile environments, but technology continually extends survival beyond natural limits. Even the expanding universe, while dynamic and evolving, does not immediately carry the nearest star beyond our reach. Taken alone, each problem feels difficult but negotiable. Together, they feel different. Imagine for a moment that humanity solves propulsion. Suppose we design an engine capable of accelerating a spacecraft to 10% of the speed of light. That achievement alone would redefine civilization. At that velocity, Proxima Centauri would be roughly 42 years away from Earth's perspective. A single human lifetime could encompass a one-way mission. That sounds manageable, at least compared to 70,000 years at Voyager's speed. But propulsion does not exist in isolation. To reach 10% of light speed, the energy requirement becomes enormous. Kinetic energy increases with the square of velocity. Raising speed by a factor of 10 increases energy demand by a factor of 100. The spacecraft must not only accelerate, but also decelerate upon arrival. That effectively doubles the required energy budget. Every kilogram of shielding, habitat structure, life support, and fuel must be accelerated and then slowed again. Mass becomes the central constraint. Shielding against radiation and dust adds weight. Weight increases propulsion demands. Propulsion systems require reinforcement. Reinforcement adds further mass. Each solution compounds the next. Now consider the environment at high velocity. At everyday speeds, interstellar space is almost empty. At relativistic speeds, it becomes something else entirely. Even a microscopic dust grain encountered at 10% of light speed carries enormous kinetic energy. Collisions that would be insignificant at Voyager's velocity become catastrophic at relativistic fractions. Shielding must be thick enough to absorb impacts. Thick shielding increases mass. Increased mass demands more energy. The cycle tightens. Even if we assume perfect engineering, relativity introduces temporal separation. At 10% of light speed, time dilation is modest but measurable. The crew would age slightly less than observers on Earth. At higher velocities, the effect becomes more dramatic. At 50% of light speed, time slows noticeably for the traveler. At 90%, it slows profoundly. A crew might experience only a handful of years while decades pass at home. A journey that preserves biological life may sever continuity with origin. Reaching another star could mean returning to a world unrecognizable, if return is even feasible. Every increment in speed intensifies both the energy cost and the temporal dislocation. Add biology back into the equation. 40 years in transit requires closed-loop ecological systems approaching perfection. Air must be recycled continuously. Water must be purified without loss. Nutrients must be regenerated with minimal waste. Even small inefficiencies accumulate over decades. Entropy works slowly but relentlessly. Mechanical systems degrade, seals weaken, materials fatigue, electronics suffer radiation damage. There is no resupply, no emergency return, no repair station waiting along the way. Psychological stability becomes equally critical. Humans evolved in dynamic environments with natural variation, open skies, and social networks far larger than a ship's crew. Confinement for decades introduces strain. Communication delays grow steadily as distance increases. At 1 light year, a message requires an entire year to reach Earth. Emotional connection becomes asynchronous. Support becomes symbolic rather than interactive. Families age and pass away while signals crawl across space. Now imagine a generational mission traveling more slowly to reduce energy demand. At 1% of light speed, the journey to Proxima Centauri would take over 4 centuries. Multiple generations would be born, live, and die aboard the vessel. Cultural continuity must persist across centuries. Governance must remain stable. technical knowledge must be transmitted without degradation. The original mission must remain meaningful to individuals who have never seen Earth. History offers limited reassurance. Human societies change rapidly. Political systems evolve. Languages drift. Ideologies shift. Maintaining unified purpose over centuries within a closed environment would require extraordinary cohesion. A single prolonged conflict could fracture the mission irreversibly. Even if such a society remains stable, the destination itself may not cooperate. Proxima Centauri is a red dwarf star prone to intense stellar flares. Planets within its habitable zone orbit close to the star and may be tidally locked. Radiation environments could be harsh. Colonization might require additional shielding and infrastructure, increasing complexity upon arrival. Each barrier alone remains technically conceivable. Together, they amplify risk beyond comfortable margins. And the universe does not remain static while we plan. The solar system orbits the center of the Milky Way at roughly 220 kilometers per second. Proxima Centauri follows its own galactic orbit. Over tens of thousands of years, relative positions shift. The local interstellar medium changes density as we move through different regions. The heliosphere expands and contracts with solar activity cycles. The environment through which any interstellar vessel travels is not constant. Even if we solved propulsion, energy, and biology, we would be navigating a moving system within a moving galaxy inside an expanding universe. The expanding cosmos introduces a subtle but important perspective. On the largest scales, regions of the universe are already receding from us faster than light due to the expansion of space itself. No spacecraft could ever reach them. While Proxima Centauri remains gravitationally bound and therefore not subject to this particular fate, the principle is instructive. Accessibility is conditional, timing matters, delay has consequences. If humanity waits millions of years before attempting interstellar travel, stellar positions will have shifted significantly. Proxima Centauri will not occupy the same relative coordinates. Stars pass near one another on cosmic timescales. The nearest star is not a fixed label but a dynamic relationship. Now imagine the cumulative weight of all constraints. To reach Proxima Centauri within a human lifetime requires high velocity. High velocity demands immense energy. Immense energy requires massive propulsion systems and shielding. Massive systems require structural resilience and redundancy. Long-term missions require ecological and sociological stability. Sociological stability must persist without external intervention. Biological resilience must withstand radiation and confinement. Relativity alters temporal continuity. The galaxy continues to evolve. The universe continues to expand. None of these factors independently forbids the journey. But together, they narrow feasibility into a razor-thin corridor. It is possible that a sufficiently advanced civilization could engineer its way through that corridor. It is also possible that the convergence of these constraints renders the endeavor impractical, even if not theoretically impossible. The universe does not actively prevent us from trying. It simply refuses to simplify the path. And this convergence forces a different kind of reflection. When we imagine reaching the nearest star, we often imagine triumphs humanity stepping onto alien soil. But the deeper question may not be whether we can get there. It may be whether we remain meaningfully connected to ourselves once we attempt it. Because to cross that gulf, we would need to transform propulsion, restructure society, extend biology, and accept temporal separation. The mission would not merely be technological, it would be civilizational. At that point, the barrier ceases to be distance alone. It becomes an identity. The nearest star tempts us because it appears within reach. It shines like any other star in the night sky. It suggests possibility, but possibility does not guarantee practicality. If all barriers converge, then perhaps the more profound question is not whether we will reach another star, but what reaching it would cost. And when that cost is examined closely, something quieter begins to emerge. Perhaps the greatest value of the stars is not in touching them physically, but in understanding the limits they reveal. Because sometimes the most important discovery is not how far we can go. It is where reality gently reminds us to pause. For all our speculation about propulsion systems and interstellar ambitions, there is only one object humanity has ever sent beyond the boundary of our solar system. It is not a starship. It is not a crewed vessel. It is a machine built in the early 1970s. Voyager 1. Launched in 1977 on what was originally planned as a 5-year mission to study Jupiter and Saturn, Voyager 1 has now traveled for nearly half a century. It has passed the outer planets, crossed the termination shock, and moved beyond the heliopause into interstellar space. Today it drifts more than 150 astronomical units from the Sun, over 14 billion miles away. That sounds far, but perspective changes everything. 1 astronomical unit is the distance between Earth and the Sun, about 93 million miles. The heliopause, the boundary where the Sun's influence fades and interstellar space begins, lies roughly 120 astronomical units away. Voyager crossed that boundary in 2012. After traveling for 35 years, it had just barely left the Sun's protective bubble. Now consider this: Proxima Centauri is approximately 268,000 astronomical units away. Voyager has covered about 150. That means after nearly 50 years of continuous travel, humanity's most distant spacecraft has completed roughly 0.05% of the journey to the nearest star. At its current speed of about 38,000 miles per hour, Voyager would require roughly 73,000 years to reach Proxima Centauri, and that assumes it were heading in that direction, which it is not. 73,000 years. When Voyager launched, the internet did not exist. When it reaches even 1% of the distance to Proxima, every civilization that exists today will be gone. Languages will have evolved beyond recognition. Borders will have shifted countless times. Our current era will be a distant archaeological memory. Voyager is not traveling slowly by ordinary standards. It is moving faster than any human-made object in history, and yet, against interstellar distances, that speed becomes almost irrelevant. The scale does not bend. Voyager's journey teaches us something fundamental about leaving the solar system. Crossing the heliopause did not mean escaping the Sun entirely. Beyond the heliopause lies the Oort cloud, a vast, spherical shell of icy bodies thought to extend from roughly 2,000 astronomical units to perhaps 100,000 astronomical units. Voyager has not yet reached even the inner edge of this cloud. At its current speed, it may take several hundred years just to enter it, and tens of thousands of years to exit it. In other words, even after leaving the heliosphere, Voyager remains gravitationally bound to the Sun for an immense stretch of time. The solar system is not merely a set of planets orbiting a star. It is a gravitational domain that extends far beyond Neptune. To truly leave, it requires more time than any civilization has ever endured. This reality reframes our ambitions. When we talk about reaching another star, we often imagine departure as a singular moment, a clean break from the Sun's influence. Voyager reveals that leaving is not abrupt. It is gradual. It is extended. It unfolds over decades and centuries. Even more revealing is Voyager's technology. The spacecraft carries computers with a total memory measured in kilobytes. Its transmitter is weaker than a household light bulb. Its power source is a radioisotope thermoelectric generator fueled by decaying plutonium, steadily losing output each year. Engineers must regularly shut down instruments to conserve energy. Eventually, in the late 2020s or early 2030s, Voyager's power will be insufficient to communicate. It will fall silent. But silence does not mean it stops. Voyager will continue drifting for millions, perhaps billions of years. It will orbit the center of the Milky Way along with hundreds of billions of stars. It It will pass near other stars, not close enough to enter their systems, but near enough to shift its trajectory slightly. It will wander through interstellar space long after humanity itself may no longer exist. And yet, despite its longevity, Voyager is a probe. It carries no humans. It requires no life support. It does not suffer isolation or radiation in the way biological organisms do. Its simplicity is its strength. This highlights another truth about interstellar travel. Sending machines is profoundly easier than sending people. Probes can be small. They can endure radiation with hardened electronics. They can travel at higher velocities without concern for gravity simulation or food production. Even so, Voyager's journey illustrates the scale problem vividly. If our most distant probe, traveling for half a century, has barely begun the trip, what does that imply for human vessels with far greater mass and complexity? Some have proposed sending miniature probes propelled by powerful lasers, gram-scale spacecraft accelerated to significant fractions of light speed. Such missions could, in theory, reach Proxima Centauri within a few decades, but these probes would not slow down upon arrival. They would pass through the system at tremendous velocity, transmitting fleeting data before vanishing into the darkness beyond. They would not carry humans. They would not establish colonies. They would be reconnaissance, not migration. Voyager also teaches us about the environment between stars. Its instruments measured the density, temperature, and magnetic fields of the interstellar medium. The space between stars is not empty. It contains sparse atoms, dust particles, and cosmic radiation. At Voyager's speed, collisions with these particles are negligible. At higher velocities, they become consequential. The deeper lesson is this: the interstellar medium is real. It has structure. It has variability. It is not a blank canvas across which spacecraft glide effortlessly. Any future mission must account for these conditions. Voyager's data provide our only direct measurements of this environment. Without them, we would still rely entirely on theoretical models. And yet, even Voyager's discoveries came with surprises. Scientists predicted where the heliopause would lie. They were wrong by billions of miles. They predicted its shape. They were wrong again. They expected a clean transition into interstellar space. Instead, Voyager encountered complex structures and dynamic oscillations. If our models of our own solar boundary were imperfect, what confidence can we place in our models of interstellar travel at far greater scales? Voyager's greatest contribution may not be its distance, but its humility. It demonstrated that even our local cosmic neighborhood defies tidy predictions. The boundary of the solar system was farther out than expected. Its structure was asymmetric. Its magnetic behavior contradicted assumptions. This matters because interstellar travel depends on accurate modeling. Small miscalculations compound over light years. A boundary misjudged by a few astronomical units is trivial within the solar system. A trajectory misjudged by a fraction of a degree across interstellar space becomes catastrophic. Voyager's drift also underscores the tyranny of time. 50 years of travel have carried it 150 astronomical units. That achievement required extraordinary engineering, global cooperation, and sustained funding. And yet, in the context of 268,000 astronomical units to Proxima Centauri, it is barely measurable. When we imagine interstellar travel, we often compress timelines. We picture launches and arrivals within human frames of reference. Voyager forces us to confront the actual timescales involved. It has traveled longer than many space agencies have existed. It will take tens of thousands of years to pass within even a light year of another star. Leaving the solar system is not a dramatic leap. It is a slow unraveling of gravitational ties over centuries. Reaching another star is not an extension of planetary exploration. It is an entirely different regime of scale. There is something poetic about Voyager carrying the golden record, a curated selection of sounds and images representing Earth. The record was intended as a message in a bottle, a testament to human existence. The probability that another civilization will ever encounter it is vanishingly small. Space is too vast. The galaxy is too sparsely populated. But the symbolic gesture remains powerful. Voyager is proof that humanity can send artifacts into interstellar space. It is also proof of how small those artifacts become against galactic distances. If a probe traveling for 50 years has barely begun the journey, what does that imply for vessels burdened with the mass of human life? If crossing our own heliosphere required decades, what will crossing the interstellar gulf demand? Voyager does not declare interstellar travel impossible. It does something subtler. It recalibrates expectation. The nearest star is not unreachable because it is hidden. It is unreachable because scale itself resists compression. And when scale resists compression, ambition must confront patience. The machine continues outward, silent and steady. It has no destination in mind. It will never reach Proxima Centauri. It will drift past other stars at distances measured in trillions of miles. It will carry its golden record long after the last signal fades. Its journey reveals a truth that no equation alone can convey. Leaving is easy to imagine. Reaching is another matter entirely. And somewhere in that difference lies the quiet boundary between what we hope for and what the universe allows. So far, we have treated interstellar travel as a problem of physics. We have looked at distance and discovered that even the nearest star sits beyond any intuitive human scale. We have examined energy and found that the cost of speed rises exponentially. We have stepped into relativity and learned that the universe itself enforces a limit on how fast matter can move. We have confronted biology and seen how fragile human bodies become outside Earth's protective environment. And we have widened the lens to cosmic expansion, realizing that the universe is not static but evolving. Each barrier is formidable on its own. But there is one more constraint that does not appear in equations or astrophysical models. It is the lifespan of civilizations. Interstellar travel is not merely a technical undertaking. It is a temporal commitment. It requires a civilization to remain stable, coherent, technologically capable, and economically functional across stretches of time that exceed most of human history. Human civilization in its technological form is astonishingly young. Agriculture emerged roughly 10,000 years ago. Writing systems developed perhaps 5,000 years ago. The scientific method that underpins modern physics is only a few centuries old. The industrial age spans roughly 200 years. The space age itself is less than 70 years old. Voyager has been traveling for nearly 50 years, and even that feels extraordinary by human standards. Now compare that timeline to the journey to the nearest star. At 10% of the speed of light, Proxima Centauri would be roughly 42 years away. That is barely within a single human lifetime. At 5%, it stretches to more than 80 years. At 1%, it becomes more than 4 centuries. At Voyager's speed, it requires tens of thousands of years. The mismatch is stark. Empires rise and fall in less time than even optimistic interstellar missions would require. Political systems transform within decades. Nations fracture, merge, reform, and dissolve. Languages evolve beyond recognition in 1,000 years. Religious systems emerge and fade. Economic structures shift with technological change. Even the most stable societies in recorded history have struggled to maintain institutional continuity beyond a few centuries without profound transformation. Now imagine initiating a mission that will not arrive for 400 years. The scientists who design the propulsion system will not live to see the spacecraft leave the heliosphere. The engineers who assemble it will not witness its arrival. The political leaders who authorize it will be long forgotten. The culture that launched it may not exist in recognizable form when the ship reaches its destination. This is not a failure of ambition. It is a reality of time. Interstellar travel demands continuity beyond precedent. It demands that funding remain stable not for election cycles, but for generations. It demands that scientific knowledge be preserved accurately without distortion across centuries. It demands that infrastructure remain functional without catastrophic interruption. It demands that a civilization survive not just economically, but politically and socially for a sustained period of coordinated effort. History offers limited reassurance. Consider how often knowledge has been lost. The formula for Roman concrete disappeared for centuries. Ancient astronomical records were destroyed in wars. Libraries burned. Scientific progress stalled during prolonged instability. Technological expertise can vanish within a generation if not actively maintained. Even in the modern era, research programs are routinely canceled or restructured due to shifting political priorities or economic downturns. Interstellar travel is not a one-time expenditure, it is a civilizational trajectory. Beyond routine instability lies existential risk. Humanity faces statistically real threats: asteroid impacts, global pandemics, nuclear escalation, ecological collapse, and technological miscalculation. The probability of any one catastrophic event in a given decade may be small, but across centuries, cumulative probability grows. If an interstellar mission requires uninterrupted stability for 400 years, the likelihood that no major disruption occurs during that span becomes increasingly fragile. Some researchers have described this dynamic as a civilization half-life. Just as radioactive material decays over time, complex societies appear to exhibit structural instability over long durations. Political fragmentation, economic inequality, environmental strain, and technological disruption accumulate. The longer the timeline, the higher the probability of destabilizing events. Interstellar travel assumes not just survival, but sustained focus. Now widen the lens further. Even if humanity avoids extinction, it may not remain culturally coherent. Technological acceleration is reshaping civilization rapidly. Artificial intelligence, biotechnology, automation, and digital networks are transforming how humans interact, govern, and define identity. In a few centuries, the definition of human may shift dramatically. Biological humans may integrate with digital systems. Consciousness may partially or fully detach from organic substrates. If that occurs, the motivation for sending biological crews across light years may diminish. Digital probes, artificial agents, or data transmissions may suffice. Exploration may become informational rather than physical. The desire to physically colonize another star system could fade if presence can be simulated or transmitted virtually. This introduces another Alternatively, technological civilizations may be inherently unstable. Advanced capabilities introduce new vulnerabilities. Artificial intelligence misalignment, biotechnology accidents, energy mismanagement, or autonomous systems failures could destabilize societies in ways difficult to predict. If such vulnerabilities increase with technological complexity, the very maturity required to attempt interstellar travel may simultaneously elevate existential risk. The Fermi paradox sharpens this tension. If the galaxy contains hundreds of billions of stars and potentially billions of habitable planets, where are the visible signs of interstellar expansion? One plausible explanation is not that interstellar travel is physically impossible, but that it is practically unsustainable. Civilizations may arise, develop technology, and then either collapse or transform before achieving the sustained stability required to cross interstellar distances. In that sense, time becomes a filter. The universe may allow travel in principle, but civilizations must endure long enough, remain coherent enough, and prioritize expansion strongly enough to execute it. Now consider the inverse. Suppose humanity achieves unprecedented stability. Suppose we transition to sustainable energy systems, manage environmental risks, reduce conflict, and preserve scientific continuity across centuries. Suppose we eliminate most existential threats and develop long-term institutional resilience. Even then, interstellar travel remains a gamble. It consumes enormous resources. It demands extraordinary coordination. It introduces permanent separation between origin and destination. A colony around Proxima Centauri would be separated from Earth by years of communication delay. Over generations, cultural drift would accelerate. Shared governance would become impossible. The two branches of humanity would evolve independently. Interstellar expansion is not simply growth, it is divergence. And divergence introduces uncertainty. Over centuries, the colony would develop its own identity, shaped by its environment and isolation. Earth would continue evolving separately. Communication delays measured in years would prevent real-time coordination. Political unity across light years becomes implausible. Cultural coherence dissolves into parallel histories. This is not necessarily negative, it is simply reality. But it reframes interstellar travel as something more than exploration. It becomes a civilizational fork. When we combine this civilizational dimension with the physical barriers we have already examined, the corridor narrows further. Distance demands speed, speed demands energy, energy demands mass, mass demands engineering resilience, relativity distorts time, biology strains under radiation and isolation, expansion alters cosmic conditions, civilization must endure without catastrophic disruption for centuries. Each barrier amplifies the others. None alone forbids the journey. Together, they approach something close to impracticality. This does not mean humanity is incapable of extraordinary feats. We have repeatedly overcome obstacles once thought insurmountable. But interstellar travel is not comparable to crossing an ocean or landing on the moon. It is a sustained alignment across physics, biology, economics, psychology, and time. It requires more than innovation. It requires continuity. And continuity across deep time is rare. The nearest star remains where it is. It does not flee. It does not resist. It simply exists at a scale that magnifies every vulnerability we carry. If interstellar travel fails to occur, it may not be because the universe forbade it. It may be because civilizations rarely remain coherent long enough to attempt it. Time becomes the silent arbiter. The longer the journey, the higher the probability that something intervenes: political instability, economic collapse, technological regression, or transformation of identity itself. Interstellar travel may not be impossible in principle. It may be filtered in practice. And that realization forces a deeper question. If the nearest star remains physically reachable but practically unattainable, what does exploration become? Does our inability to cross that gulf diminish us, or does it redefine ambition itself? Because perhaps the most profound truth is this: the barrier between us and the stars is not a single wall. It is the convergence of limits that test not only our technology, but our endurance as a species. The stars are patient. The question is whether we are. After examining distance, energy, relativity, biology, cosmic expansion, and the fragile continuity of civilization, the conclusion begins to feel heavy. None of the barriers alone absolutely forbids reaching another star. Yet together, they form a narrowing corridor that may be too thin for any civilization to pass through. If that is true, if the nearest star remains beyond our practical reach, then what does exploration become? For centuries, exploration meant movement. It meant ships crossing oceans and caravans crossing deserts. It meant planting flags and drawing new maps. Expansion was physical. To explore was to arrive. But the scale of the universe forces a different interpretation. The stars are not continents waiting for settlement. They are separated by distances that strain the limits of endurance. If arrival becomes unlikely, then exploration must be redefined. The first shift is from presence to understanding. Voyager never reached another star. It never entered another planetary system. Yet it transformed our knowledge of the outer solar system and interstellar space. It discovered active volcanoes on Io, hinted at oceans beneath Europa's ice, revealed the intricate structure of Saturn's rings and measured the properties of the interstellar medium for the first time. It expanded our mental map of reality without carrying a single human passenger. Exploration, then, may not require bodies crossing space. It may require information crossing space. When we launch telescopes like the James Webb Space Telescope, we are exploring without moving ourselves physically. We gather photons that have traveled billions of years. We decode spectra that reveal atmospheric composition of exoplanets. We detect gravitational waves from black hole mergers. We reconstruct cosmic history from faint signals. This kind of exploration is not lesser, it is simply different. The human instinct to explore is often framed as territorial, as expansionist, but curiosity itself does not require colonization. It requires access to information, and information travels at the speed of light. If the speed of light is a barrier for spacecraft, it is also a bridge for knowledge. A signal from Proxima Centauri takes 4.24 years to reach us. That delay is inconvenient for conversation, but it is negligible for scientific discovery. Data returned from a probe orbiting Proxima Centauri b would arrive years after transmission, but years are short compared to the centuries required for physical arrival. This reframes the ambition. Perhaps interstellar travel will not begin with human migration. Perhaps it will begin with probes, autonomous, lightweight, capable of accelerating to high velocities and transmitting compressed data back to Earth. Miniature spacecraft propelled by lasers have already been proposed. At small mass scales, reaching significant fractions of light speed becomes more feasible. Such probes could cross the Gulf in decades, gather data during brief flybys, and send back streams of information. They would not carry settlers, but they would carry knowledge. Another shift involves time perspective. Human civilization measures achievement in decades. The universe operates in millions and billions of years. When we ask whether we will reach another star, we often imagine doing so within a timeframe meaningful to us. But what if exploration unfolds on longer arcs? Suppose humanity persists for 1,000,000 years. Suppose technology continues evolving. 1,000,000 years is short compared to the age of the galaxy. In that span, propulsion systems may improve dramatically. Materials science may yield breakthroughs we cannot currently imagine. Artificial intelligence may design spacecraft beyond current constraints. Biological forms may adapt intentionally rather than naturally. The nearest star remains 4.24 light-years away. That distance does not change, but our capabilities might. However, even here, caution is necessary. Civilizations do not necessarily scale smoothly across millennia. The assumption of uninterrupted progress may be as unrealistic as assuming immediate breakthroughs. Deep time cuts both ways. It allows for advancement, but it also increases the probability of regression or collapse. So exploration must adapt to uncertainty. There is another dimension to consider. We often frame interstellar travel as a necessity for survival. The argument suggests that humanity must spread beyond Earth to avoid extinction. If one planet fails, another can preserve the species. But the distances involved make this strategy less practical than it appears. Establishing a colony within our own solar system, on Mars, the Moon, or artificial habitats, is far more achievable than crossing light years. Redundancy within a single star system may suffice for species preservation for millions of years. If survival does not require interstellar travel, then the motivation shifts back toward curiosity. And curiosity does not demand immediate arrival. There is also the question of meaning. If the stars remain unreachable, does that diminish us, or does it redefine the scale at which we operate? The pale blue dot photograph captured Earth as a tiny speck suspended in a sunbeam. From billions of miles away, our entire civilization vanished into a pixel. That image did not inspire despair. It inspired humility. It reframed importance. It reminded us that scale does not negate significance. If the nearest star remains beyond reach, our exploration may turn inward rather than outward. The ocean depths remain largely unexplored. The human brain remains only partially understood. Consciousness itself is still a mystery. The quantum structure of reality continues to challenge theoretical physics. Dark matter and dark energy remain largely unexplained. There are frontiers closer than Proxima Centauri. Exploration is not synonymous with expansion. It is synonymous with inquiry. There's also the possibility that reaching another star is not a binary outcome. Perhaps humanity will never send a crewed vessel to Proxima Centauri. Perhaps we will never establish a colony there. But perhaps we will build instruments that allow us to map its planetary system in extraordinary detail from afar. Perhaps we will simulate its surface environments with high fidelity. Perhaps we will send probes that skim its orbit and transmit data for years. Reaching the stars physically may be impractical. Understanding them deeply may not be. And there is something profound in that distinction. The universe may impose physical limits on movement. It does not impose limits on comprehension. Even if we remain confined to our solar system, our knowledge of the cosmos can continue expanding. Telescopes can peer deeper into time. Detectors can capture subtler signals. Mathematical models can refine our understanding of spacetime itself. The speed of light restricts matter. It does not restrict thought. This leads to another subtle realization. Interstellar travel is often imagined as the ultimate expression of human ambition, but perhaps the greater achievement is sustaining curiosity in the face of limitation. To accept that some distances may remain practically unreachable does not mean surrendering wonder. It means recalibrating it. There is also the possibility that the barrier itself shapes our identity. Constraints foster creativity. The fact that we cannot reach another star easily has driven innovations in propulsion theory, materials science, radiation shielding, and astrophysics. The difficulty of the problem has enriched science rather than impoverished it. If interstellar migration proves impractical, humanity may instead channel its ambition into building resilient civilizations within the solar system. Artificial habitats around the sun could support trillions of people. Energy from the sun vastly exceeds current consumption. Terraforming projects, orbital megastructures, and advanced computational networks could flourish within our stellar neighborhood for millions of years. In that scenario, the galaxy remains distant, but our capacity for complexity and meaning remains vast. And still, the question lingers. If the stars remain physically distant, why do they feel so important? Because they symbolize transcendence. They represent the possibility of exceeding our origins. They remind us that we are part of a structure far larger than ourselves. Even if we never step onto another world orbiting another sun, the act of contemplating it expands our mental horizon. The barrier between us and Proxima Centauri may never collapse, but it has already reshaped how we see ourselves. Exploration then becomes less about arrival and more about orientation. It becomes about situating humanity within the cosmos accurately and honestly. It becomes about acknowledging scale without surrendering significance. If we cannot reach another star within a human lifetime, that fact forces patience. If we cannot reach it within a century, that fact demands civilizational maturity. If we cannot reach it at all, that fact invites humility. Humility does not diminish ambition, it refines it. The nearest star remains where it has always been, a faint red dwarf shining quietly in the darkness. It does not move closer because we desire it. It does not retreat because we doubt ourselves. It simply exists. The question is no longer whether we can cross the gulf immediately. The question becomes whether the journey itself, the pursuit, the calculation, the attempt, already fulfills something essential within us. Because perhaps the most meaningful aspect of interstellar travel is not reaching another star. It is recognizing the scale of the universe and choosing to think about it anyway. And in that choice, something subtle but powerful occurs. We stop measuring ourselves by how far we can physically go. We begin measuring ourselves by how deeply we can understand. The stars remain distant, but the act of reaching toward them, even in thought, changes us. And that change may matter more than arrival. There is something deeply unsettling about the idea of a limit. Human history has conditioned us to believe that every boundary is temporary. Mountains were once barriers until we learned to cross them. Oceans were once insurmountable until we built ships. The sky itself was unreachable until we invented flight. Even the moon, which for most of history was a symbol of distant impossibility, eventually bore human footprints. So when we look at the nearest star and feel the weight of its distance, our instinct is not to accept it as unreachable. Our instinct is to assume that, given enough time and ingenuity, we will overcome it. But what if this time is different? What if the barrier between us and the nearest star is not simply another challenge awaiting a clever solution? What if it represents something more fundamental, not just a technological limit, but a structural boundary embedded into the nature of reality? To understand what that would mean, we need to shift the question. Instead of asking whether we can reach another star, we should ask what reaching it would require, not just technically, but civilizationally and philosophically. Interstellar travel is often framed as the next inevitable step in human expansion. The narrative is familiar. We explored continents, then oceans, then airspace, then the moon. The next frontier must be the stars. But this narrative assumes continuity. It assumes that technological growth scales upward smoothly, that ambition compounds, and that civilization remains stable long enough to execute its dreams. History does not necessarily support that assumption. Human civilization, as a technological entity, is astonishingly young. Agriculture appeared roughly 10,000 years ago. Writing systems developed perhaps 5,000 years ago. Modern science, the structured mathematical understanding of the physical universe, is only a few centuries old. The industrial age spans around 200 years. The space age, less than 70. In that context, even a 40-year journey to another star is enormous. A 400-year journey stretches beyond anything humanity has ever sustained coherently. Political systems rarely remain stable for centuries without dramatic transformation. Empires collapse, ideologies shift, economic models evolve, even languages mutate beyond recognition across 1,000 years. Interstellar travel is not just a matter of building a ship. It is a matter of sustaining intention across deep time. Imagine beginning a mission that will arrive 4 centuries after launch. The scientists who design it will not see its completion. The engineers who assemble it will not witness its arrival. The political leaders who authorize it will fade into history long before it leaves the heliosphere. The culture that conceived it may not survive in recognizable form. This is not a technological barrier. It is a temporal one. Interstellar travel demands continuity across generations, scientific, economic, and cultural continuity. Funding must persist. Knowledge must remain accurate and accessible. Infrastructure must endure. Catastrophic disruption must not intervene. Civilizational stability must be strong enough to absorb wars, pandemics, political upheavals, and environmental stress without collapsing. History suggests that such sustained alignment is rare. Even in the modern era, major scientific initiatives are vulnerable to shifting priorities. Space programs expand and contract with economic cycles. Political administrations redirect funding. Research is canceled or delayed. Interstellar travel would require not just enthusiasm, but unwavering commitment across centuries. And beyond routine instability lies existential risk. Asteroid impacts remain statistically possible. Global pandemics can destabilize societies. Climate systems can shift. Artificial intelligence and biotechnology introduce unprecedented variables. Even absent catastrophic events, gradual environmental degradation or resource scarcity can constrain economic growth. The longer the timeline, the higher the cumulative risk. If an interstellar mission requires 400 years of uninterrupted progress, the probability that nothing destabilizing occurs during that span becomes increasingly fragile. Civilization must not merely survive, it must remain technologically coherent. This introduces what some thinkers describe as a civilization filter. The idea is simple. Many civilizations may arise, but few persist long enough to execute multi-century, resource-intensive projects. The universe may not forbid interstellar travel, but time may quietly filter out attempts. The Fermi paradox sharpens this perspective. If the galaxy contains hundreds of billions of stars and potentially billions of habitable planets, why do we see no clear evidence of widespread interstellar colonization? One possibility is that interstellar travel is far more difficult than simple energy calculations imply. Civilizations may reach technological maturity, but fail to maintain stability long enough to expand meaningfully. Time becomes the silent arbiter. But even if humanity achieves unprecedented stability, if we solve environmental crises, manage existential risk, and sustain scientific institutions across centuries, interstellar travel remains a gamble. Consider the opportunity cost. The energy required to propel even a modest spacecraft to 10% of light speed would be immense. The infrastructure necessary to produce and store that energy would reshape global priorities. Resources devoted to interstellar ambition might otherwise be invested in planetary resilience, habitat construction within our own solar system, or advancements in computation and medicine. Is it rational to commit centuries of effort to a single star system when our own solar system contains vast potential? The sun will shine for billions of years. Energy available from it dwarfs humanity's current consumption. Artificial habitats could be built in orbit. Terraforming projects could reshape nearby worlds. The Kuiper Belt and Oort Cloud contain immense material resources. Within one star system, civilization could expand in complexity without expanding in distance. This reframes expansion. Interstellar travel is not the only path to growth. Another dimension complicates the issue further: identity. Reaching another star does not merely extend territory, it bifurcates civilization. Communication delays measured in years prevent real-time coordination. Cultural drift accelerates. Political unity across light years becomes implausible. A colony around Proxima Centauri would evolve independently. Over centuries, language, norms, and biological adaptations could diverge. Interstellar travel may not unify humanity. It may fragment it. That fragmentation is not inherently negative, but it alters the narrative. Expansion is no longer simply growth, it becomes divergence. Now consider the psychological dimension. Humans derive meaning from connection to place, to history, to community. Leaving Earth permanently is not just relocation, it is severance. A one-way journey to another star would require accepting that return may never occur. Families left behind would age and die, while signals traverse the void. The travelers would inhabit a timeline increasingly disconnected from their origin. The deeper we examine the problem, the clearer it becomes that interstellar travel is not just a technical hurdle, it is a civilizational transformation. It demands that we become something more stable than we have ever been. Perhaps something more patient. And here, the meaning of the limit begins to shift. If the nearest star remains beyond our practical reach, does that diminish us? Or does it clarify us? The pale blue dot image showed Earth as a tiny speck suspended in a sunbeam. That image did not diminish humanity, it humbled us, it recalibrated importance, it reminded us that scale does not erase meaning. Similarly, the realization that we may never physically stand on a planet orbiting Proxima Centauri does not erase the stars. It reframes exploration. Exploration is not synonymous with conquest. It is synonymous with understanding. The speed of light limits matter. It does not limit thought. Every photon arriving from Proxima Centauri carries information. Spectroscopy reveals atmospheric composition of distant planets. Telescopes detect stellar flares and magnetic activity. We can model orbital mechanics and simulate climates without stepping onto alien soil. In some sense, we have already reached other stars, not physically, but intellectually. This may be the deeper truth. The universe permits comprehension more readily than colonization. The stars remain distant in space, but they are accessible in knowledge. Perhaps the limit is not an insult to ambition. Perhaps it is a teacher. Limits force creativity. They refine priorities. They demand that we consider what truly matters. If we cannot reach another star within a human lifetime, perhaps we must learn to think beyond lifetimes. If we cannot expand physically, perhaps we expand intellectually. If we cannot cross light years, perhaps we deepen our stewardship of the world we already inhabit. The nearest star remains 4.24 light-years away. It shines quietly, indifferent to our ambitions. The question is not whether it is there. The question is whether our desire to reach it reflects necessity or longing. And perhaps the most profound realization is this: the barrier between us and the stars is not merely distance. It is maturity. The universe does not forbid us. It simply demands that we become worthy of crossing its scale. And whether we will ever meet that demand remains uncertain. The stars are patient. They will shine for trillions of years. The question is whether we can endure long enough and wisely enough to greet them. For decades, we have imagined interstellar travel as a dramatic event, a launch, a burst of acceleration, a starship piercing the darkness and vanishing into the distance. But the only real example humanity has of leaving the solar system tells a very different story. Voyager did not burst into interstellar space. It drifted there, slowly, patiently, over decades. Launched in 1977, Voyager 1 was designed for a 5-year mission to explore Jupiter and Saturn. No one expected it to still be operational half a century later. Its computers contain less memory than a modern calculator. Its transmitter produces about 23 watts of power, weaker than a small household light bulb. Its radio signal, stretched across billions of miles, arrives on Earth as one of the faintest signals ever routinely detected by human technology. And yet, it continues to move. Today, Voyager 1 is roughly 160 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Multiply that by 160, and you get a distance that sounds enormous by human standards. But that is only the beginning. To leave the solar system, Voyager had to cross the heliopause, the boundary where the Sun's solar wind finally yields to the pressure of the interstellar medium. Scientists once believed that boundary lay around 90 to 100 astronomical units from the Sun. They were wrong. Voyager crossed it at about 121 astronomical units, billions of miles farther out than predicted. Even then, leaving was not a clean moment. It was gradual. The magnetic field did not behave exactly as expected. The density of particles shifted in subtle ways. The boundary breathed inward and outward as solar storms rippled through space. It took 35 years just to reach that edge. And yet, even after crossing it, Voyager had not truly left in the way we imagine leaving. Beyond the heliopause lies the Oort cloud, a vast spherical shell of icy bodies that may extend from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units. Voyager has not yet reached even the inner edge of that cloud. At its current speed of about 38,000 miles per hour, it may take centuries just to enter it. To exit it could take tens of thousands of years. Now consider this carefully. Proxima Centauri, the nearest star beyond our Sun, lies roughly 268,000 astronomical units away. Voyager has traveled about 160. That means that after nearly 50 years of uninterrupted travel, humanity's most distant spacecraft has covered less than 0.1% of the journey. At its current speed, Voyager would take about 73,000 years to reach Proxima Centauri. 73,000. When Voyager finally travels even 1% of that distance, every nation that exists today will be gone. Every language spoken today will have changed beyond recognition. The buildings we call permanent will have eroded into sediment. Voyager is not slow by engineering standards. It is fast beyond anything our ancestors could have imagined. But against interstellar distance, its speed becomes almost irrelevant. This is what leaving actually looks like. Not cinematic acceleration, not dramatic departure, but an incremental crawl measured in millennia. Voyager also teaches us something about endurance. Its longevity comes from simplicity. Its systems were overbuilt by necessity. Redundancy was built into critical components. Engineers designed it to survive the unknown, and still its power supply is fading. Each year the plutonium fuel decays a little more. Instruments are shut down to conserve energy. Heaters are turned off. The spacecraft grows colder. By the early 2030s, it will no longer have enough power to transmit. It will fall silent. But it will not stop. It will continue drifting for millions, perhaps billions of years, orbiting the center of the Milky Way along with hundreds of billions of stars. It may pass within a light year or two of other stars over tens of thousands of years, but it will never slow down. It will never enter orbit. It will never settle. It will simply wander. Now imagine replacing Voyager with a human vessel. Not a 1,800-pound probe, but a spacecraft massive enough to sustain life. A vessel containing shielding against cosmic radiation, rotating habitats to simulate gravity, closed ecological systems to recycle water and air, agricultural modules for food production, redundant engineering systems for decades of operation. Every kilogram of that mass must be accelerated. Every kilogram must be decelerated. Every kilogram multiplies the energy demand. Voyager survives because it needs nothing but power for its instruments. A crewed vessel would need air, water, food, temperature control, waste processing, medical capability, psychological stability, and continuous maintenance. The difference in complexity is not incremental. It is exponential. Even at 10% of light speed, the journey to Proxima Centauri would take about 42 years from Earth's perspective. That means 42 years of exposure to interstellar radiation, 42 years of maintaining life support without resupply, 42 years of isolation from Earth, with communication delays stretching into months and eventually years. If the vessel intends to decelerate upon arrival, it must carry additional fuel, doubling energy requirements. If it intends to return, the timeline extends to nearly a century. And that assumes no system failures. Space is not forgiving of mechanical fragility. On Earth, when infrastructure fails, we repair it. When a part breaks, we manufacture a replacement. When supply chains falter, we reroute them. An interstellar vessel would operate in permanent isolation. Every component must function without external support. Every subsystem must anticipate failure. Voyager's simplicity allowed it to endure. A human starship would not have that luxury. There is also the interstellar medium itself. Space between stars is often imagined as empty. It is not. It contains sparse hydrogen atoms, helium, dust particles, and cosmic rays. At Voyager's speed, collisions with these particles are insignificant. At 10% of light speed, Even microscopic dust grains carry enormous kinetic energy. A single grain of sand impacting at relativistic velocity could release energy equivalent to an explosive. Shielding mitigates risk. Shielding adds mass. Mass increases energy demand. Energy demand increases system complexity. And complexity introduces new vulnerabilities. Voyager reveals something sobering. Even leaving our own solar system required decades. It revealed that our models of the heliopause were incomplete. Scientists predicted its location. They were wrong by billions of miles. They predicted a smooth transition. They found unexpected structures like the magnetic highway, where particle flows behaved in ways no model anticipated. If we misjudge the boundary of our own star's influence, how confident can we be about modeling the environment across light years? Interstellar travel is not simply about reaching another star. It is about surviving every unknown along the way. There is also a psychological dimension. Voyager carries the golden record, a disk containing sounds and images of Earth. It was never expected to be found. The probability of another civilization encountering it is vanishingly small. The galaxy is too vast. The spacecraft is too small. It is not aimed at any specific star. And yet we sent it. That act matters. It reveals something about us. Voyager is not proof that we can conquer the stars. It is proof that we are compelled to reach toward them. But the difference between sending a probe and sending people is enormous. Voyager requires no gravity, no air, no emotional resilience, no governance, no generational continuity. It drifts quietly, indifferent to time. A human mission would not have that indifference. The nearest star remains 4.24 light-years away. Voyager demonstrates that even with half a century of travel, we have barely begun to close that gap. It forces us to recalibrate ambition. Leaving the solar system is not a singular moment. It is a process measured in decades. Reaching another star is not a bold leap. It is a civilizational marathon measured in centuries. If Voyager, our most durable machine, requires 73,000 years to reach Proxima Centauri at its current speed, what does that imply about our expectations? It implies that interstellar travel is not an extension of planetary exploration. It is an entirely different regime of scale. The universe is not hostile. It is simply vast. And vastness resists compression. We are used to solving problems by moving faster. Interstellar space punishes speed with energy demand, radiation risk, and collision hazards. We are used to building redundancy into systems. Interstellar travel magnifies complexity until redundancy itself becomes a liability. We are used to measuring progress in decades. Interstellar travel demands patience across centuries. Voyager's journey reveals a fundamental truth. The stars are not close. They only appear that way. The distance between suns is not like the distance between continents. It is more like the distance between galaxies in miniature. When we speak casually about going to the stars, we compress scale into narrative. Voyager uncompresses it. It reveals the gulf in its raw proportions. The machine drifts outward, silent but persistent. It will outlast nations. It may outlast humanity. It may circle the galaxy long after our sun has evolved beyond its current state. It carries music and greetings, images and diagrams, a quiet declaration that we existed and wondered. But it does not carry colonists. It does not carry expansion. It carries perspective. And that perspective may be the most important cargo of all. Because perhaps the true cost of leaving is not fuel. It is time. Not seconds or years, but civilizational time. The patience to endure, the stability to persist, the humility to accept scale. Voyager shows us what leaving actually means. Not triumph, not conquest, but drift. The nearest star remains where it is. The question is no longer whether it is reachable in theory. The question is whether we can sustain the alignment required to reach it in practice. And that is not a question of propulsion. It is a question of who we are and how long we remain that way. If we may never reach another star, then the future of humanity may not unfold across light years. It may unfold here, within a single solar system. That statement can feel disappointing at first. The imagination resists confinement. For centuries, we have trained ourselves to think of progress as expansion. New lands, new oceans, new frontiers. The stars became the final frontier almost by cultural instinct. If we exhausted Earth, we would move outward. If our sun aged, we would migrate. The story seemed linear. But the physics we have explored does not bend to narrative. The nearest star remains 4.24 light-years away. That distance does not shrink because we desire it to. The energy curves do not soften. The speed of light does not relax. The biological fragility of human bodies does not disappear simply because ambition persists. The civilization filter does not guarantee endurance. So if we remain here, within our solar system, what does that actually mean? First, it means scale is misunderstood. Our solar system is not small. Even confined within the sun's gravitational influence, the domain available to humanity is vast beyond everyday comprehension. The distance from the sun to Neptune is roughly 30 astronomical units. Beyond that lies the Kuiper belt, extending to perhaps 50 astronomical units. Beyond that, the scattered disk, and farther still, the Oort cloud, stretching tens of thousands of astronomical units into darkness. If we cannot cross 4.24 light-years, we still have access to tens of thousands of astronomical units. Within this region, there are asteroids containing metals and rare elements. There are icy bodies holding water. There are moons with subsurface oceans. There are dwarf planets. There is energy from the sun, immense, steady, and lasting billions of years. The sun produces roughly 3.8 times 1026 watts of power. Human civilization currently consumes around 2 times 1013 watts. The difference is staggering. Even a tiny fraction of the sun's output would sustain civilization far beyond current consumption levels. Solar collectors placed in orbit could harvest energy continuously without atmospheric interference. Dyson-like structures, while speculative, illustrate the magnitude of potential energy capture. Even partial megastructures could support trillions of people if engineered sustainably. Remaining within one star system does not imply stagnation. It implies depth. Instead of spreading thin across interstellar voids, humanity could expand in complexity within its own gravitational neighborhood. Artificial habitats could orbit the sun in stable configurations. Rotating space stations could simulate gravity indefinitely. Resources from asteroids could fuel construction. Closed ecological systems refined in deep space could sustain life long-term. The limiting factor would not be energy. It would be coordination. If interstellar travel is constrained by physics, intrastellar expansion is constrained by governance and foresight. Building resilient habitats requires stability. Harvesting resources responsibly requires long-term planning. Preventing ecological collapse requires disciplined management. In other words, the barrier shifts inward. The stars may remain distant, but our own system offers room for growth. There is also another possibility. If physical expansion across light years is impractical, perhaps intelligence evolves differently. Biological humanity may not remain the dominant mode of cognition indefinitely. Advances in computation, neural interfaces, and artificial intelligence suggest a future where cognition is not exclusively tied to organic brains. If consciousness can be digitized or augmented, the constraints of biology shift. Digital entities require less mass, less shielding, less food, less gravity. They can tolerate radiation differently. They can exist in distributed networks rather than confined habitats. In such a future, the ambition to cross interstellar space may transform. Instead of transporting bodies, we may transmit information. Instead of colonizing planets, we may seed probes that carry compressed archives of knowledge and self-replicating systems. Instead of migrating, we may project. But even here, the speed of light remains. Signals still require years to traverse light years. Real-time interaction remains impossible across interstellar distances. Identity fragments across delay. The solar system may become the stable base, while probes and signals extend outward gradually. Another scenario is even more introspective. Humanity may choose not to expand physically at all. The drive to colonize other stars often rests on fear of extinction, fear of planetary collapse, fear of eventual solar death. But the sun will shine for roughly 5 billion more years. That is 50 million times longer than recorded human history. Within that window, there is time to solve planetary sustainability. There is time to adapt. There is time to evolve. The urgency for interstellar escape is often overstated relative to immediate challenges. If humanity learns to live sustainably within its own star system, the stars may remain objects of study rather than migration. There is also a psychological dimension to confinement. Humans historically resisted limits because limits implied stagnation, but modern science reveals that growth does not require outward expansion. Complexity can increase inwardly, knowledge can deepen, art can evolve, societies can refine governance structures, consciousness itself can expand in sophistication. Remaining within the solar system does not equate to remaining primitive. It may instead represent a mature acceptance of scale. Now consider the cosmic timeline. The universe is approximately 13.8 billion years old. The Milky Way formed over 13 billion years ago. Earth formed 4.5 billion years ago. Life emerged relatively quickly thereafter. Intelligent life capable of building radios and rockets appeared extremely recently on cosmic scales. If intelligent civilizations are rare, and if the window during which they attempt interstellar travel is narrow, then the galaxy may remain largely uncolonized, not because it is impossible, but because it is rare for species to align long enough to attempt it. In that context, remaining within a single star system may be the default outcome for most civilizations. The Fermi paradox, the apparent silence of the galaxy, may not indicate absence of life. It may indicate that interstellar colonization is extraordinarily difficult in practice. Perhaps the universe is filled with isolated civilizations contained within their own stellar neighborhoods, expanding in complexity rather than geography. If that is true, then the stars remain separate not because of hostility, but because of scale. There is something quietly beautiful in that. Each star becomes a self-contained story. Each system evolves independently. The galaxy becomes a mosaic of isolated civilizations, separated not by war or rivalry, but by the simple geometry of space. In such a universe, exploration becomes observational rather than migratory. Telescopes become bridges, data becomes connection, understanding becomes the currency of expansion. The inability to physically reach another star does not diminish the universe. It preserves its structure. There is also a humility in accepting limits. For centuries, humans assumed that every frontier would eventually yield. The continents yielded, the oceans yielded, the sky yielded, the moon yielded, but perhaps not every boundary is meant to collapse. Some may exist to define scale. If the stars remain distant, they remain aspirational. They remain reminders that reality is larger than ambition. And ambition is healthier when tempered by reality. Now imagine humanity in 10,000 years. Even without reaching another star, civilization could transform dramatically. Energy systems could stabilize, ecological damage could be repaired, habitats could be built in orbit, Mars and other worlds within our system could host outposts, knowledge of physics could deepen. Consciousness could evolve. Within a single star system, there is room for trillions of lives. Within a single galaxy, there is room for endless contemplation. The question then becomes not how far can we go, but how well can we endure. The nearest star may remain beyond reach. But endurance within one star system may be the true test of maturity. Perhaps the deepest realization is this: the universe does not require us to spread. It requires us to understand. And understanding may not demand movement across light years. It demands patience, curiosity, and resilience. The stars remain where they are. They shine steadily, indifferent to whether we ever stand beneath them. If we never cross the gulf between suns, it will not be because we lacked imagination. It will be because scale itself demanded a different kind of growth. And that growth may occur not outward, but inward, within our own systems, within our own consciousness, within the quiet persistence of a civilization that learns to live sustainably under a single star. The nearest star is not an insult to our ambition. It is a measure of our scale. And perhaps the true frontier is not across light years. It is across time. There is a quiet realization that emerges when we step back from the engineering diagrams and energy equations and simply look at the sky. The universe does not need us. The stars were burning billions of years before humanity appeared, and they will continue burning long after our species changes beyond recognition or disappears entirely. Proxima Centauri will shine for trillions of years. The Milky Way will rotate slowly around its center. Galaxies will collide and merge. None of these events depends on whether humanity ever builds a starship. The cosmos is not waiting for us to arrive. It unfolds according to its own physics, indifferent to ambition. That indifference can feel unsettling. Human history has trained us to assume that boundaries are temporary. Mountains were obstacles until we crossed them. Oceans were barriers until we sailed across them. The moon was unreachable until we stood upon it. Every frontier in our past eventually yielded. So when we encounter the gulf between stars, we instinctively assume it must also yield. But the distance to the nearest star is not like the distance across an ocean. It is not measured in days or months. It is measured in decades at best, and centuries or millennia more realistically. The scale is not merely larger, it is categorically different. The nearest star sits 4.24 light-years away. That number seems modest when spoken aloud, but a light-year is nearly 9.5 trillion kilometers. Multiply that by 4.24 and you arrive at over 40 trillion kilometers. Voyager, traveling for almost 50 years, has covered only a tiny fraction of that span. At its current speed, it would take roughly 73,000 years to arrive. That is older than agriculture, older than cities, older than written language. The distance is not just large, it is civilizationally destabilizing. It exceeds any timeline within which human institutions have ever operated coherently. If the universe does not need us, then reaching another star is not a requirement imposed from outside. It is an ambition generated from within. We project meaning onto the stars because they represent transcendence. They symbolize expansion beyond limitation. But the cosmos does not promise accessibility. It permits movement within the boundaries of physics, and those boundaries are strict. The speed of light does not bend. Energy curves do not soften. Radiation does not pause because we wish it to. The universe remains consistent, not accommodating. And yet, the fact that the universe does not need us does not diminish us. It reframes us. The significance of humanity cannot depend on occupying more territory. It must depend on something else, something internal rather than geographic. Consciousness is rare. As far as we know, the vast majority of the universe is unaware of itself. Stars burn without reflection. Galaxies spin without interpretation. Black holes merge in silence. Human beings, however, can measure those processes. We can calculate stellar lifetimes. We can model cosmic expansion. We can detect gravitational waves from events billions of light years away. That capacity for understanding is extraordinary. Perhaps exploration is not defined by arrival. Perhaps it is defined by comprehension. We have already extended our perception across light years through telescopes and detectors. The James Webb Space Telescope analyzes atmospheres of exoplanets without leaving Earth's orbit. Radio arrays capture faint signals from pulsars and distant galaxies. Spectroscopy reveals chemical compositions of stars far beyond physical reach. Information travels at light speed, even if bodies cannot. In that sense, knowledge collapses distance more efficiently than propulsion ever could. There's also a different form of expansion available within a single star system. The Sun produces roughly 3.8 times 1026 watts of power. Humanity currently consumes about 2 times 1013 watts. Even harvesting a tiny fraction of solar output would sustain civilization for billions of years. Artificial habitats could orbit the Sun. Asteroids could provide raw materials. Closed ecological systems could be perfected. The Kuiper Belt and Oort cloud contain immense resources. Remaining within our solar system does not imply stagnation. It implies depth rather than breadth. It suggests growth inward, in complexity, resilience, and sustainability. Another possibility complicates the narrative further. Human identity may not remain biological indefinitely. Advances in artificial intelligence, neural interfaces, and computational substrates hint at futures in which cognition is not bound to fragile organic bodies. If consciousness becomes partly or fully digital, the barriers of radiation and gravity shift. Smaller, lighter probes could carry informational patterns rather than flesh, but even then, the speed of light remains. Communication delays stretch across years. Coordination becomes asynchronous. Expansion transforms into branching rather than conquest. The universe's indifference invites humility. If we cannot reach another star within our lifetime, that does not imply failure. It implies calibration. It reminds us that scale matters. The cosmos operates across millions and billions of years. We operate across decades. That mismatch does not erase meaning. It clarifies it. We are a brief flare of awareness in a vast timeline. The fact that we can comprehend that timeline at all is extraordinary. Whether we step onto another planet, orbiting another star, may matter less than whether we continue to understand our place within the one we inhabit. Limits shape identity. The speed of light, gravity, entropy, these are not adversaries. They are structural truths. By confronting them honestly, we refine our ambitions. Instead of assuming that expansion is inevitable, we ask whether endurance is possible. Instead of chasing territory, we pursue stability. If interstellar travel remains impractical, the challenge shifts towards sustaining civilization responsibly within our own system. The stars cease to be prizes. They become perspective. Imagine humanity 10,000 years from now. Perhaps we never built a crude starship. Perhaps we never crossed the gulf between suns. But perhaps we perfected ecological balance within our solar system. Perhaps we eliminated preventable suffering. Perhaps we built stable societies that endure across centuries. Perhaps we deepened our understanding of physics and consciousness. Perhaps we cultivated art and culture that reflect cosmic awareness. In that scenario, failure to reach another star does not represent smallness. It represents maturity. The nearest star remains where it has always been, a faint red dwarf glowing quietly in the darkness. It does not beckon, it does not retreat, it simply exists. The barrier between us and it is not a punishment, it is a measure of scale. The universe does not need us to cross that barrier, but we may need it to understand ourselves. Whether we ever touch another sun physically is uncertain. What is certain is that the act of contemplating that distance reshapes our sense of proportion. The stars are patient. They will shine for trillions of years. The question is not whether they need us. The question is how we choose to live beneath them. So we arrive at the end of this journey through space and time, through physics and philosophy, through distances that stretch beyond comprehension and barriers that may never fully yield. We have examined 5 fundamental obstacles standing between us and the nearest star. Distance revealed itself not as a simple gap to cross, but as a gulf measured in scales that exceed human intuition. Energy demands showed us that speed comes at costs that multiply faster than our capacity to generate power. Relativity reminded us that the universe enforces limits we cannot negotiate away. Biology confronted us with fragility, bodies built for one world struggling to endure in environments never meant for them. And time, perhaps the quietest barrier of all, showed us that civilizations rarely persist long enough to execute dreams measured in centuries. Each barrier alone is formidable. Together, they form something more than obstacles. They form a structure, the architecture of reality itself. And that structure may not be hostile, but it is uncompromising. The nearest star sits 4.24 light-years away. That number has not changed throughout this exploration. It will not change tomorrow. Proxima Centauri continues to shine as it has for billions of years, a small red dwarf accompanied by at least one planet, indifferent to whether humanity ever learns to cross the distance between us. We may never stand on that world. We may never feel the light of another sun warming our skin. But we know it exists. And that knowledge, quiet and invisible, connects us across the void in ways that matter deeply. Exploration is not defined only by arrival. It is defined by understanding. Every telescope pointed toward distant stars extends our perception. Every photon captured carries information from places we may never physically touch. Every equation modeling the structure of spacetime brings us closer to comprehending the universe we inhabit. We are explorers already, not with ships crossing light years, but with minds crossing boundaries of ignorance. If the stars remain beyond physical reach, they do not become less significant. They become teachers. They reveal scale. They impose humility. They remind us that some limits are not temporary obstacles waiting for clever solutions, but permanent features woven into the fabric of existence. And accepting that does not diminish us. It grounds us. It shows us that meaning does not require conquest, that wonder persists even when arrival remains uncertain, that the act of contemplating vast distances, of calculating, modeling, and imagining already transforms us in ways that matter. The barrier between us and the nearest star is not cruelty. It is calibration. The universe is showing us what we are: small, brief, fragile, within a cosmos so vast and ancient that our entire existence registers as less than a heartbeat. And yet, within that heartbeat, we have learned to see. We have measured distances across billions of light years. We have detected gravitational waves from black holes merging in the early universe. We have analyzed the atmospheres of planets orbiting distant suns. We have built models of cosmic evolution stretching from the Big Bang to the heat death of everything. Consciousness is rare, perhaps vanishingly rare. And whether it spreads across the galaxy or remains concentrated here, within one solar system orbiting one ordinary star, it remains extraordinary. The stars do not need us to touch them. They need only that we see them clearly. And we do. Every night when darkness falls, the stars emerge. Proxima Centauri shines faintly among them, steady and patient. It has burned for billions of years. It will continue for trillions more. It does not know we wonder about it. It does not care whether we ever arrive. But we know it is there. And in knowing, we are changed. So as this exploration draws to a close, let the weight of these ideas settle gently. The universe is vast beyond measure. Time stretches farther than civilizations endure. Distance resists compression. Energy follows laws that do not bend for ambition. And yet, none of this erases meaning. It clarifies it. We are not diminished by limits. We are defined by how we respond to them. The nearest star may remain distant for centuries, millennia, or forever, but the act of reaching toward it in thought, in calculation, in wonder, has already accomplished something profound. It has reminded us that we are part of something larger. That reality operates on scales we did not design and cannot fully control. That some boundaries teach rather than defeat. And that understanding, even without arrival, is a form of connection. So rest now. Let the stars continue their silent vigil above. Let Proxima Centauri shine in the darkness, unreachable but visible, distant but known. Let the universe unfold according to its own vast rhythms, indifferent to our timelines, but permitting our presence within it. You have traveled far tonight, not across space, but across thought. You have confronted distances measured in trillions of kilometers. You have examined energy curves that rise toward infinity. You have stepped into relativity and felt time bend. You have faced the fragility of biology and the instability of civilizations. And in facing these truths, you have grown. Not in territory, but in perspective. The barrier remains. The stars remain distant. But you are no longer the same person who began this journey. You see scale more clearly now. You understand limits more honestly. You recognize that wonder does not require possession, only awareness. So close your eyes. Let the weight of the day dissolve. Let the questions settle into quiet acceptance. The universe will continue without you tonight. Stars will burn, galaxies will rotate, space will expand, time will flow forward, patient and unstoppable. And when you wake, the stars will still be there. Proxima Centauri will still shine, 4.24 light-years away, exactly where it has always been. Unreachable, perhaps, but never forgotten. Sleep now. Let distance become dreamlike. Let energy equations fade into the background. Let relativity blur into abstraction. Let the barriers we examine tonight become part of the vast, quiet knowledge you carry, not as burdens, but as understanding. The nearest star remains. And so do you. Small within the cosmos, but capable of seeing it. Brief within time, but capable of measuring it. Fragile within reality, but capable of comprehending it. Rest well. The stars are patient. They will shine tomorrow. And the universe, vast and indifferent, will continue to allow you to wonder. Good night. The journey inward begins when the journey outward pauses. Sleep deeply. The stars will wait.